All right, so here is our second example of how to find the area between given regions. And this one is a little bit more complex, where we'll for sure need to figure out where our points of intersection are. So we want the common interior of r equals 3 sine theta and r equals 2 minus sine theta. So again, we want to graph this first. And if we graph it, there's a picture of it. So I have 3 sine theta. That's the first equation, and I'm going to press on 3 so that it graphs it for us. And then our second region is 2 minus sine theta. And when we graph this, we get that first circle is a 3 sine theta. This bottom circle will be 2 minus sine theta. All right, so as long as we have a general sketch of that, we're going to be okay. And I like to have the sketch drawn. So here, my top equation, or my top graph, excuse me, is r equals 3 sine theta. And the bottom graph, if we look at it, it starts out at 2, and it's going to intersect up there a little bit, but it doesn't have to be. Oh, and I like to do this in a different color. So there's that one. Obviously, it doesn't have to be a great graph, but it's good to look at where our points of intersection are, and also when we look at our radial lines, what graph we're ending at. So we know we have these 2 points of intersection which we need to find, and why we need to find that is right now, if I start with my radial lines and I'm looking for my common interior here, well, if I start with a radial line of 0, my common interior is going to this the graph that's black, which relates to 3 sine theta. And that is true until I hit this point of intersection. So basically what I was drawing in there is all radial lines, and now I hit this point of intersection. Well, from here, if I keep looking at my radial lines, now I've switched equations, or graphs, and now I'm ending at the red graph. So I have to take that into account. What graph are you ending at with your radial lines? And I'm going to use symmetry, so I'm going to stop there. Well, the first thing that we have to do is, in order to solve this, is set our 2 equations equal to each other and figure out our points of intersection. So 3 sine theta is going to equal 2 minus sine theta. Add the sine theta over, so that will give us 4 sine theta is equivalent to 2. Obviously divide by 4, which is 1/2. When does sine of theta equal 1/2? Well, that will be when theta is equal to pi over 6 and 5 pi over 6. I'm going to use symmetry, so 5 pi over 6 won't really matter. But this looks like it's even that pi over 6. So that's, I always like to check, like, does it look accurate? And yes, this one does. So basically, when I start then and I want to find my area, I am going to use symmetry, so I have 2, and then I know that my area formula has that 1/2 in there. And I like to just double check that if I plug in a 0 here, I should have 0 for an answer. I'm plugging it, remember, into the black, the equation, that the black equation here that relates to that black graph. So if I plug in a 0, sine 0 is 0 times 3 is 0, so perfect. That's not going to go anywhere, and then I have my radial lines. So 0 to pi over 6, and that equation is 3 sine theta, that quantity squared, differential theta. Well, now I need to add to it the second part of this. And I'm just going to make this one red just to start for the first step, I guess. Again, symmetry, because we have here, and then basically it would be symmetric right here. So I have 2 times my formula, well, that's 1/2. I start at pi over 6 now, so I'm ending at the red graph, which would relate to the red equation. And I'm assuming I'm going to end at pi over 2. And I'm going to check, if I plug pi over 2 into my red equation, sine pi over 2 is 1. 2 minus 1 is 1. So that makes sense. At pi over 2, I have the r value as 1. So then I end at pi over 2. I need my equation, 2 minus sine theta, and that has to be squared. So the setup really here is the big thing. Can you set it up? Do you know the 2 parts to it? Do you know where your point of intersection is? For that first part of it, what equation are you using? And so that's what graph are your radial lines ending at if you are looking for your common interior. And the second portion then, the second part of this, obviously now we're ending at the red graph, which relates to 2 minus sine of theta. And so that setup is a really big key thing. What I typically do now is I just solve for one integral and then I'll solve for the other one next instead of keep continuously going back and forth. So obviously we have addition here, we're adding them together, so I'm just going to draw a line going down. I'm going to deal with this side first and get my answer, and then I'll deal with the right side. So when I look at this, obviously 2 times 1/2 will give me 1. I'm integrating from 0 to pi over 6. If I square things, 3 squared is 9, but I'm going to factor that constant out. And then I have sine squared theta differential theta. Well, now I know when I integrate sine squared or cosine squared, I have to use our double angle. And this one would be 1/2 minus, because it's sine, it's cosine, double our angle. Well, it's theta right now, so it's 2 theta. That portion also has to be divided by 2. And there's different ways you could factor out that 2 in the denominator if you'd like. So there's not one specific way that you have to go through and solve this. Oops, I probably should, I need to have another integral for this one because I have to have a u value. That angle has changed. So what I'm going to do here is, I think I'm just going to squeeze an integral in. And technically we should have a differential theta here. So to make it fitted in there without having everything be too crammed up, make it smaller. Here I definitely want to factor out the 1/2 to start. If our u value is 2 theta, differential of u will be 2 differential theta. So I need to take out a 2, that's going to make that a 4. And now I can integrate this. So antiderivative of 1/2 will give me 1/2 theta, remember in terms of theta, minus 1/4, that becomes u. Antiderivative of cosine is sine. Our u value is 2 theta, and that is from 0 to pi over 6. Fundamental theorem of calculus. Plug in our pi over 6. Pi over 6 times 1/2 will give us pi over 12. We'll put parentheses for this first one. And then if we plug in pi over 6, that will give us pi over 3. Sine of pi over 3, or sine of 60 degrees, is square root of 3 over 2. So we have square root of 3 over 2, but it's also times that 1/4, so that will make that divided by 8. So there's if I plug in pi over 6, fundamental theorem of calculus tells us to subtract. If I plug in a 0, I get 0 minus 2 times 0 is 0. Sine of 0 is 0. So for this first half, our answer, 9 pi divided by 12, will give us 3 pi divided by 4 minus 9 square root of 3 divided by 8. And we'll have to take this portion of it and add it to what we get on the right side. Just be really conscious and careful about this portion. If you need to make another step out of it up here where you're trying to throw that u value in, make sure that you can see everything. All right, so now when I solve the right side, we have from pi over 6 to pi over 2. We need to expand this, so we have 4 minus 4 sine theta plus sine squared theta differential theta. Again, like usual, we're going to get sine squared, which is really annoying. And what we can do is, for this one, there's so many different ways that you can do this with notation. I'm going to leave the first 2 terms because I don't need a u value. And then with this next part, I know that it's 1/2. I'm going to make that differential theta minus, I know that I would have cosine 2 theta divided by 2, so I'm going to take out the 1/2. That's going to be hard to fit in that screen. And so oftentimes I just break it up right away And I know, do I have the formula? Yeah, it's 1 minus cosine of 2 theta all over 2, so I have covered everything. Here we know that our u value is 2 theta. Derivative of u is 2 differential theta. I needed 2. I need to take out a 1/2. That makes that another 4. And then that would be u there. Now I think I can integrate everything. Everything on this side, we're integrating from pi over 6 to pi over 2. So from here, this will give us 4 theta minus 4 antiderivative of sine is negative cosine, so that becomes a positive cosine theta, plus 1/2 theta minus 1/4 antiderivative of cosine is sine, 2 theta. This is pi over 6 to pi over 2. And now plugging everything in. If I plug in pi over 2, 4 pi divided by 2 is 2 pi. Plus cosine of pi over 2 is 0. So that term is 0. Plus, now this will be pi over 4 minus sine, 2 pi over 2 is pi. Sine of pi is 0. Now I have to, fundamental theorem of calculus, subtract if I plug in pi over 6. Well, 4 pi over 6 is 2 pi divided by 3. Plus cosine of pi over 6. Pi over 6 is at 30-degree angle, so that would give us square root of 3 over 2 times 4. I'll just put that in. 4 square root of 3 divided by 2. Obviously, that makes it 2 square root of 3. And make sure that's right. Cosine of pi over 6. Yeah, that's good. And then we'd have adding to that pi divided by 12 minus, now I have 2 times pi over 6, which will give me pi over 3. Sine of pi over 3 is square root of 3 over 2. Multiply it by a 4, so I have square root of 3. Instead of over 2, it's divided by 8. And so on this side, I can start to put my like terms together. So what I would do, I have 2 pi, pi over 4, minus 2 pi over 3, plus pi divided by 12. I guess here I would just take my calculator out and add up all the coefficients. So I have 2 plus a fourth, so 0.25, minus 2/3, and plus 1/12. And that should be good. Make that as a fraction. Probably could have done that in our heads. We have 5 pi divided by 3. So I've accounted for those terms. Then this is minus 2 square root of 3. And that would become now plus minus a negative square root of 3 divided by 8. And remember, I want to put these two terms, I have to add these two terms together. So because they all can, well, we have the square root of 3, square root of 3, square root of 3, we can get a common denominator and put those together as well. So we have 3 pi over 4 plus 5 pi divided by 3. So 3/4. Oh, I can take this, just the 5/3, and add to it. Oops. Add to it the 0.75. And as a fraction, 29/12. And that would be our pi. So we have 29 pi divided by 12. And now here, because they all have the square root of 3, I want to put them together, but I have to get a common denominator. Well, these two already have a denominator of 8, so here if I have to get a denominator of 8 multiplied by 8 over 8, that'll give us 16/8. So now we can look at this, and we have a negative 9/8. And that would be our square root of 3, we'll just stay with it, minus our 16/8, which we know is 2. And we can add to it our 1/8. So that gives us, in the long run, negative 3. But remember, that's negative 3. Oops, I'll go back to red. Negative 3 square root 3. That's our common interior, so that is our units squared. So, pretty fun problem there. But be careful. The setup is really key. Obviously, if the setup isn't right, it's going to be incredibly difficult to get the right answer. But there's so much that goes on in here. There's a lot of little things that you have to be very conscious about. Moving on, if we have arc length, so we have arc length, we talked about area, a lot of things with area, and now we have arc length and then the area of surface of revolution. So arc length, very similar to what we have for arc length if it's rectangular or parametric. Our function, whose derivative is continuous, because we'll be using our derivative. Then the length of our graph of our polar function, obviously, from alpha to beta is given by the following. Arc length is our lowercase s. We are integrating from alpha to beta. That has to be given. And again, for arc length, just like for the other equations, it's a square root. And it is our function, the original function, squared, plus the derivative of the function squared. So it's really nice. I guess another way that you could write this, alpha to beta, it's the square root of r squared plus derivative of r squared differential theta. So easy equation to remember. With arc length, just like for rectangular and for parametric, you're going to have a lot of situations where you're going to end up using your calculator, because here everything is under the radical. So what we know how to integrate, chances are pretty good we'll have to use our calculator to solve this. All right, so for an example, we want to find the length of our curve over the given interval. We have the equation r equals 8 times 1 plus cosine of theta, and from 0 to 2 pi. So then arc length, okay, it's 0 to 2 pi. And what I would do is go through this and say, well, what is r equal to? And I know r is equal to 8 plus 8 cosine theta. Well, before I plug it into the equation, I know I have to square this. So then usually I square it right away, and I'll say, okay, I have 8 times 8 is 64. Then I'll have, well, that'd be a 64 cosine theta plus 64 cosine theta, which will give us 128 cosine theta plus 64 cosine squared theta. So there is our function squared. So we have 64 plus 128 cosine theta plus 64 cosine squared theta. This will be one heck of an integral. Now when I take the derivative of my original function, remember my original function here is 8 plus 8 cosine theta, and I would distribute that 8 so that you don't have to use your product property for your derivative. Oops, so this is r prime now. The derivative of 8 is 0. The derivative of 8 cosine 0 will give us negative 8 sine 0, or sine theta, sorry, it definitely is a theta. And now I have to square my derivative. When I square it, we create 64 sine squared theta. So we're adding to this 64 sine squared theta differential theta. Well, what we can do is, obviously we have a 64 that we can factor 64 out of here. We can factor a 64 out of all of our terms. And so doing that, we have 64 times 1 plus 2 cosine theta plus cosine squared theta plus sine squared theta differential theta. Now properties of radicals, because we've created multiplication here, this term times that whole thing, I can take the square root of 64. So, and I can take that out. So square root of 64 is 8, and I want to factor that out as the 8. The other thing that we see here is we have cosine squared plus sine squared, which you should be looking for. And we know that this portion of it, that's equivalent to 1. And we never like to have the combination of sine and cosine. So that's really nice because then we can simplify and we get rid of the sine in there and we get sine squared and cosine squared. So 64 is gone. We have 1 plus 1. Remember that's equivalent to 1. So we have 2 plus 2 cosine theta differential theta. And from here we could potentially factor out another 2. I don't really care at this point if you do or if you don't. No matter what, we're not going to be able to integrate this because if our u value is cosine of theta, well, I don't have a sign here, so I can't just multiply in a variable. So once you simplify, and I'll tell you to simplify the integral, but from here you do have to use your calculator. So to find arc length, we need to graph this. And when we graph this, we need to go back to rectangular. Well, okay, there's a couple ways that you can graph it, and we'll look at both ways. You can graph this in rectangular, or you could graph your original. Either one, it'll work out. So here, if I graph it as a function in rectangular, y would equal the square root 2 plus 2 cosine theta, parenthesis, should end that. And my window setting has to be from 0 to 2 pi. So that's good. I'll go to 10 here, 2 pi, 6 something. And now when I graph it, I get that cycloid now graphing. And now I can go to calculate, second calculate. We want to into our integral. We want this from 0, our lower limit. Our upper limit would be 2 pi. And we'll have it graph. Our answer is 8. Remember we have this 8 out here, so this gives us an arc length of 64 units. So we just have to go back. If you're using this equation, you have to go back to rectangular mode in order to graph that. We can go and, where did that equation go? If we looked at our original, I think that we can do this. This is kind of a guess here. I think that we can keep this in polar. Never mind. We can't do that. You'd have to have a TI-86 calculator because TI-86s have exactly our to calculate arc length. So you cannot do this unless you have a TI-86, which very few have. So when you find arc length, you have to rewrite. You obviously simplify your integral. Make sure that you use that rectangular mode, which is your function mode, when you're looking for arc length. So pretty easy formula. That's not too bad to do. The last thing, area of surface of revolution. Again, we have a function. Our derivative is continuous on our interval from alpha to beta. The area of the surface formed by revolving the graph of our polar equation from alpha to beta about our indicated lines are as follows. So if we rotate about our polar axis, well, we know our polar axis is our x-axis. Area of surface of revolution. We still have that 2 pi, which we've had for all of them. So nothing changes there. It's alpha to beta. And in this situation, we need our function. So whether you call it r, we'll write it as r. But we know r is equal to f of theta. And then this has to be times sine theta. Then it's multiplied by our arc length. So our function squared plus the derivative of our function squared differential theta. So a lot of it is very similar. Why this is sine is if I'm going about our polar axis, so here is our polar axis. Remember, sine is your y value, and so we always want like what that radius is, so that's why that would be y. If I rotate about the line where theta is pi over 2, this is pi over 2. So if I'm looking for my radius, that would be my x value, and cosine represents x's. So the slight change then, 2 pi, we're going from alpha to beta. It's your function times, now this one would be cosine of theta. Because remember, that represents basically your x's. Sine up here represents your y's. Times our arc length. So, our function squared plus derivative of our function squared. This will all be in terms of theta. And these you can usually, I'll probably give you one that you have to go through and solve and show your work for it. So we want to find the area of the surface formed by revolving this curve, r equals a times 1 plus cosine of theta, about our polar axis from 0 to pi. A is just a constant. So keep that in mind in here. A is a constant. It can be any number. But now what this does is say, well, whatever number that is, we can quickly figure out what the area of surface is with our answer. So to set up our equation, if I'm going about our polar axis, we have 2 pi. We're integrating from 0 to pi. I need my equation first. And our equation here is a times 1 plus cosine theta. And now because I'm going about our polar axis, so polar axis would mean this, I want my y value, which is sine. So there's sine theta, times the square root of our function squared. So when we look at our function, we have r equals, just like our last problem, distribute the a. So it's a plus a cosine theta. I'm going to square that, which gives us, our equation squared would be a squared. This will end up being a times a would be a squared. So another one would give us 2a squared cosine theta. Took me a while to think of that. Plus a squared cosine squared theta, which is quite ugly, but very, very similar to our last problem. So if we write all of that in, we will be able to factor out the a squared here. But a squared plus 2a squared. You know what? You don't have to make it that hard, because if you just square this whole thing, you can take a squared times that squared. Then you wouldn't have the a distributed through, which would probably make a heck of a lot more sense. With the derivative, you'll want to distribute. So even though you have it written down, I won't erase it, but because your answer is not going to change here. But when I want my function squared, I need the whole thing squared. That's a squared times that squared, which is 1 plus our 2 cosine theta plus cosine squared theta. So then a squared times 1 plus 2 cosine theta plus cosine squared theta. I have to add to this the derivative, and this is where I would want to distribute. So if I distribute the a through here, my original function is a plus a cosine theta. Well, now when I take the derivative, a is a constant, so that's 0, and that would give me negative a sine theta. Remember, I have to square this. So our derivative squared is a squared sine squared theta. So when I put it up into the equation, instead of putting a squared plus sine squared theta, what I'm going to do is I know I can factor out the a squared with that one and add the sine squared theta. And there's our differential theta then. So just like our last problem that we had. All right, well, what I can do, to simplify from here, a is a constant. So I'm going to make this as simple as I possibly can, and I'm going to factor out the a. The other thing is I have the square root of a squared, which is equivalent to a, and instead of putting it right here, I'm going to again factor that out. So now I have factored out an a squared. Now I have 2 pi a squared. We're integrating from 0 to pi. And here we have 1 plus cosine of theta times our sine theta. And just like in the last problem, sine squared plus cosine squared is 1. So that gives us the 1 plus 1 is 2 plus 2 cosine theta differential theta. Well, I can make these two, I can combine them if I factor out the 2. So here I definitely want to factor out the 2. 1 plus cosine theta times sine of theta. And I guess to show the work, I have 2 times 1 plus cosine theta differential theta. Well, now I can take out, well, what does the, say I want the square root of 2. Okay, well, that's the square root of 2. I can factor it all the way out and say, okay, I take out the square root of 2. What that does is I have 2 square root of 2 pi a squared from 0 to pi, but now I can combine these two things because this, instead of as a radical, it's to the power of 1/2. So now I have 1 plus cosine theta. This is to the power of 1. This is to the power of 1/2. You have the common base of 1 plus cosine theta. I can add my exponents, and I have 3/2. And then I have the times sine theta, differential theta. Well, this is obviously very convenient because our u value can be 1 plus cosine of theta. The derivative of 1 is 0. The derivative of cosine is negative sine theta differential theta. Perfect. Put a negative there, put a negative there. And now the end is in sight. Negative 2 square root of 2 pi a squared. We're integrating from 0 to pi. This is u to the 3/2 differential u. So negative 2 square root of 2 pi a squared. When we integrate, it would be our u value, which is 1 plus cosine theta, to the 5/2 times 2/5 from 0 to pi. And you could rewrite your boundaries here in terms of u if you wanted to. I guess I didn't, so I just obviously had to go back to x. So negative 2 square root 2 pi a squared. I'm also going to factor out the 2/5, so times 2/5. Now when I plug in the pi, cosine of pi is negative 1. 1 minus negative 1, I'm sorry, 1 plus negative 1 is 0. So 0 to the 5/2 is 0. Minus, if I plug in a 0, cosine of 0, remember this is factored out, back up a step. Cosine 0 is 1. 1 plus 1 is 2. So that would give me minus 2 to the 5/2. All right, so to put things together, if I have 2 to the power of 5/2, that's the square root of 2 to the and then to the power of 5. Or I can look at it and say, well, I have 2 to the 5th first. 2 to the 5th is 32. And then I need to take the square root of it. So I think that's what I'm going to do, because that's pretty ugly if I want to start simplifying this. Now I'm going to put my outside terms here together. So I have negative 4/5. That takes care of that. Square root of 2 pi a squared times a negative, which will make that a positive. 2 to the 5th is 32, the square root of 32. Well, the square root of 32, I know 16 times 2 will give me 32. So that will give me 4 square root of 2. And these things are all multiplied together. So if I have 4 times 4 is 16, keep the fifths. Square root of 2 times square root of 2 is 2. Pi a squared, that's 32 fifths. 16 times 2 is 32 fifths. Pi a squared, area of surface of revolution, units squared. So the setup of these things, not that bad. You definitely need to practice these, and common things start to happen. If you don't practice them at all, it's going to be incredibly difficult. But to practice, you'll see very like things continue to happen, and you'll get used to how to integrate them and what to look for. So work with a partner and do the best you can. But you'll see if you follow what I have here, really the other area of surface of revolutions, I think this one is probably about as tough as they get. But this is a really good guide or reference to look back on to figure out how to do these things. So assignment for this section, not too many problems because I know that they're lengthy. Don't try to do these in 1 or 2 lines because that's not going to be possible. Obviously, I gave you a whole piece of paper for 3 of the problems. And not that you needed the whole piece of paper, but plan accordingly when you're doing your homework. And definitely get started on this tonight so you can ask questions. You can go over things tomorrow and to work with someone, because sometimes leave your setup. Don't start erasing right away. But leave your setup, because then you can see like, okay, I have the setup right. It's something when I'm integrating that just didn't work out. Or you may get far and be like, I don't know how to integrate this thing, but you have it good to there. So make sure, show your work. If you try it 1 or 2 times and you're getting frustrated, don't erase everything, leave it, and then come and check with the problem and check with the classmate to see what's going on. But good luck with it. I actually really like this section. I think it's a good challenge. And very applicable.